Okay, folks, we're back talking about the Bohr atom again. Again, this is a very simple form or model of an atom, and for years and years and years, it was, well, decades, it was assumed to be correct, and it is relatively accurate, with a nucleus of protons and neutrons and a cloud of electrons around it. But you know, what this doesn't show us is the relative distance between these subatomic particles. It looks like they're all sort of close together, but in reality, if we were thinking about this thing respectful to size, if the nucleus of this atom was about the size of a pencil eraser, the closest electron to that nucleus would be about a quarter of a mile away. So there's a lot of disparity in terms of the size of these subatomic particles and their relative distance from each other. There's a lot of empty space in an atom. So, you know, when I started studying about radiation and subatomic particles and how radiation was produced, and by the way radiation is produced is by sending a subatomic particle through the middle or through this atom and interacting with the subatomic particles within this atom. We'll get into that in more detail later too, but if you think about it, there's so much empty dead space in there. By sending a subatomic particle through here, the chances of actually interacting with it are very, very small. And in fact, that is the case. So to create any X-ray radiation, we got to send an awful lot of subatomic particles through there. It's sort of like shotgunning the thing. We're just going to have to blast it with a lot of energy and hope that eventually something will interact. But again, back to the disparity in the size of this thing. There's so much dead space in there, you've got to wonder, well, how does anything ever interact with that? And this actually was answered when I saw another picture of an atom, which makes a little bit more sense to me. It looks something like this. We can still see that it has a nucleus with protons and neutrons in there and a cloud of electrons around it, but notice that these electrons are trailing energy, an effect of energy behind them. So if we're sending a subatomic particle through here, we find out that in fact the subatomic particle that we're sending through does not have to contact these other subatomic particles to cause a reaction. So that makes a little bit more sense to me. Obviously, the closer we get to these electrons or the closer we get to the nucleus, the more effect it's going to have. But if we come in contact with the field that's left behind by these traveling electrons, and we may not have mentioned this, but obviously they're spinning around this nucleus at very, very fast speed, so chances of actually crossing paths with one of them is pretty great. So this is a better example, I think, a representation of what's going on inside the atom. Okay, a couple more definitions for us. Chemical elements and isotopes. I'll let you read chemical elements for yourself, but isotopes, like the ion that we mentioned earlier, isotopes are similar except they are missing a different subatomic particle. If you remember, ions are where we add or subtract an electron from the field. An isotope is where we change the number of neutrons in the nucleus of that atom. And we're going to talk about isotopes a little bit. We're not going to talk about them a whole lot because we actually don't use that much in medicine, but they are used in the generation of medical nuclear medicine studies. They actually inject a radioisotope into you if you're going to have a nuclear medicine study done, and the body will actually circulate that radioisotope through it, and then based on the condition of the tissues, it will emit those isotopes at different rates and things like that. They can pick that up with a gamma camera and then determine what the condition and relative condition of those tissues are. But again, isotopes, for right now, just realize that the definition of that is we're changing the number of neutrons in there. Okay, this is a picture of an ionization we talked about earlier. Positive ion on the left has fewer electrons. The negative ion on the right has more electrons. Again, electrons with a negative charge, so if we add more than normal, we end up with a negative charge or a negative ion. Two more slides here and we'll finish up. Cosmic rays, terrestrial radiation, and internally deposited radionuclides. So these are natural forms of environmental radiation. Cosmic rays come from outer space. Terrestrial radiation is long-wave radiation emitted from the Earth, And then internally deposited radionuclides are internal radiation that comes from radioactive materials that occur naturally in the human body. Believe it or not, you're radioactive to some degree. So we have naturally occurring radiation in the environment around us, and we've got to take that into consideration as well. Okay, the last slide here. This is just give you some idea of how much radiation is out there in terms of man-made radiation. And we see here that the one that obviously we're most concerned with is this medical X-rays. About 11% of all X-ray or all radiation that's created by man is from medical X-rays. Nuclear medicine, again, that's the isotopes we were talking about earlier. That's responsible for some of it as well. Consumer products, terrestrial radiation, cosmic and internal that we just talked about. And notice on the left, 55% of radiation is from radon. And I think, if I'm not mistaken, radon is a gas that occurs due to the breakdown of uranium as it ages in the earth. And you've probably heard of radon gas coming up out of the earth under your home and those kind of things. So that is a form of man-made radiation as well. But again, the one that we're most concerned about is the medical X-rays, making up about 11% of that. That's actually a pretty significant fraction of man-made radiation. So anyway, that's it for today. We'll get some more out there to you in the very near future.